All right, this is the final project presentation for the Apache group for ECE 547 Intro to Communication Networks. So as an introduction in the final project, we had a few tasks that we did. We set up a mixed wired wireless network which simulates media streams from 6 stationary mobile devices. We also configured an access point to connect to these devices via 802.11b, and we had one server connected to the access point via fast Ethernet. In our tests, we collected various network performance metrics with varying traffic loads. So as a starting point, we used the NS3 wireless module user manual. This had several guides which gave us kind of an outline of the main steps we needed to follow to create the mixed wireless wired network. This also made use extensively of topology helpers in NS3, which come with some pre-configured settings to create all the different devices at different network layers that we needed. So in a nutshell, the main steps were we created the node containers for the access point devices and server. We created and configured the Wi-Fi channel, which is the lowest layer of simulation that NS3 supports for Wi-Fi modeling, and it models the physical layer. We configured the Wi-Fi PHY layer using the default YANS Wi-Fi PHY helper. And using the Wi-Fi helper, this set up the 802.11b network devices on all nodes. We also then set up the MAC sublayer. This sets the SSID, and we can also specify the type of device. So we set up 1 access point device and 6 STA devices. Next, we configure the physical location of the devices. We use the mobility helper, where you can set as a vector the stationary position of each device. This positioning was determined by project requirements, so it's, as we can see in the figure on the right, a hexagon of an equidistant hexagon around the access point, and the access point is connected to the media server via fast Ethernet. So the network positioning, or the mobile device positioning, the X and Y coordinates were calculated according to the equation on the bottom left.
For the final stages of setup, we needed to create the media server. The server is going to be used as the final destination for all packets being sent through the access point. To do this, we create the fast Ethernet link using a CSMA helper tool within NS3. There are 2 main attributes that are needed for this tool, the first being the data rate attribute, which we set to 100 megabits per second. The second is the delay attribute set to 10 milliseconds. After this, we needed to assign the ID to the media server. There was a slight catch within our network. We need to ensure that when the packets were received at the access point, it didn't assume that it was at the destination if these two devices contain the same ID. So we had to assign 2 different subnetwork IDs. The first ID was attached to the CSMA device. The second ID was then attached to the access point. This ensured that as the packets were received, it would continue on to the server. Finally, after setting up these IDs, we assigned a UDP interface to the server, which Eric will explain why we did that.
For part 2, our team used UDP for multimedia stream transformation. And there are several reasons we use UDP. The first reason is that UDP could achieve higher throughput than TCP because it will not try to employ congestion control. And the second reason is that UDP could achieve lower delay because it will not seek to maximize the buffer up to the dropping point. And the third reason is that UDP set up congestions faster as there are no initial handshakes to set up the connections. And furthermore, UDP could transmit multicast packets, whereas TCP have to use multiple congestions. In sum, we think that UDP can be used for applications that TCP can with a proper retransformation mechanism. For part 3, we explore the maximum distance between the access point and the mobile stations with 90% packet delivery ratios, and we further explore the relationship between distance and the relationship ratio. And for the experiment setup, we set up the wireless propagation and loss model with YANS Wi-Fi channel helper, and we set the delay to to constant speed and utilize log distance in the chain of propagation and loss models. And we further set the data rate of multimedia stream to 50 kbps. And for the experimental results, as shown in the figures, we noticed that the simulation could achieve over 90% delivery ratio with 44.27 meters. And we also noticed that the delivery ratio will drop significantly if the distance is longer than 40 meters, and no package will be received if the distance is longer than 55 meters. And we think the result behind this we think the reason behind this result is if the receiver is in or inside the max range meters, the receiver could receive the transmission at the transmission power level. But if the distance beyond max range, the receivers could not receive effective power.
For part 4, the team decided to analyze the max throughput of our system. The hypothesis decided was as the packet size increases, the max throughput for the access point will also increase. The variables that we will use will be the packet size, which will increase from 500 to 1,300 bytes, each incremented by 100 bytes. The data rate, which will increase until max throughput has been decided as found. Then the RTS-CTS threshold and the simulation time will also remain constant throughout the testing. As for the testing, for each packet size being tested from 500 to 1,300 bytes, the max throughput will be considered reached when the following equation is true. Received packets over transmitted packets falls below 90%. So in other words, whenever our system has a receive accuracy below 90%, we have found the max throughput. To vary this, we will need to increase the data rate for each packet size being tested until max throughput is found. The results from our testing can be as seen. From the figure on your left, this shows the packet sizes in bytes from 500 to 1,300, and the throughput rate in megabytes per second. As you can see, as the packet size increases, our max throughput is also increasing, which proves our hypothesis as true. The fact that the overhead and the header of the packet sizes become less through the system because we're able to send more bytes at one shot rather than having to break each message into smaller packets. The display on the right also shows the packet size from 500 to 1,300 in bytes with the data rate that corresponds to each byte in kilobits per second. So as our packet size increased, we were able to increase the data rate at which we sent these packets, which also allowed for our max throughput rate to increase. For part 5, we decided to also analyze the delay and the jitter of our max throughput. So we took the results from part 4 and we wanted to look at what the delay and the jitter was doing with respect to the varying packet sizes. As you can see from the figure on the left, the delay sum of the max throughput began to decrease as the packet size increased. This corresponds to the fact that as packet sizes increased, our max throughput increased as well, meaning that the delay of our max throughput would decrease. The figure on the right is the jitter sum for our max throughput. Jitter is the rate of change for our delay of max throughput. So as you can see, as the packet size increased, our jitter began to slowly decrease from 500 bytes to 900 bytes. Then we had a sharp increase from 900 bytes to 1,000, and then began to slowly increase and change more from 1,000 bytes to 1,300 bytes.
For part 5, the variable we control is the request to send and confirm to send threshold. This threshold determines at what minimum packet size the request to send and confirm to send handshaking will take place. So any packets below this threshold will not do the three-way handshaking before being sent, and any packets above this threshold will engage in the three-way 802.11 handshake before being sent. So with our simulation, we have a fixed UDP packet size from the wireless media stations, and so this presents us with two cases. The first case is where the threshold is below the packet size, and so all packets will be above the RTS-CTS threshold, and so RTS-CTS handshaking will always take place with every single packet. The second case is that the threshold is above the packet size, in which case RTS-CTS handshaking will never occur because all the packets are the same size and they won't reach that threshold. So in the results on the right, we have two charts for varying packet sizes. The data rate was set to the maximum throughput as calculated in part 4, or earlier in part 5, discussed by Josh. So we can see from the delay sum that, or the average delay, that the smaller packet sizes below 1 kilobyte, there's a little difference between the threshold being above or below the packet size. But once we hit 1 kilobyte, there is a little bit more difference. So when the threshold is above at, say, 1,200 bytes, we get a little bit more average delay than when it's below. And this makes sense because if packets are colliding that are around 1,200 bytes, then there's a larger retransmission overhead with no RTS-CTS. But if the smaller request to send and confirm to send packets collide with each other, there's less retransmission overhead, rather. With the jitter, we can see a similar effect. Smaller packets below about 1 kilobyte, there's little effect. But the discrepancy starts to grow as we have larger packets.
One of the other network variables tested was configuring the mobile devices to use PCF or GCF. So we had 3 scenarios: no PCF, where all the mobile devices were using a distributed coordination function. And then we had one PCF scenario where we had only one node use PCF and the remaining 5 use DCF. And then we had the third scenario where we had all PCF, where there's no DCF nodes in the system. And for every scenario, since we had 6 nodes, so we had 6 flows to monitor. And for each flow, we recorded the delay sum, the jitter sum, received packets, time of first received packet, and time of the last received packet. And then we constructed the table on the right side, which is the average of each variable that we had, and then the results were as shown. So for the delay sum, we noticed that the scenario with no PCFs had the largest delay sum compared to the other two, with the one PCF and the all PCF. And the all PCF scenario had more delay than the second scenario with only one PCF. And for the jitter sum, we found that the no PCF scenario had the least jitter sum, and the one PCF and the all PCF had very close results. And for the average throughput, we found that the no PCF had significantly higher throughput compared to the all PCF, and the one PCF had the highest throughput. And taking a closer look and analyzing the reason why the throughput dropped, we found that there was a lot of the null polling happening, as we can see down here in this image at the bottom. And this wasted a lot of the bandwidth, and this is why the throughput dropped. So for the conclusion, we constructed a network with 6 Wi-Fi connected mobile devices in a hexagon shape around the access point, which was enabling the 802.11 protocol, and was connected to the media server through fast Ethernet. We also added appropriate signal power loss model to the simulation and configured the mobile devices to continuously send fixed-sized UDP packets. We also configured various 802.11 network parameters and measured the network performance. So we started by testing the distance performance of the Wi-Fi nodes with respect to the AP, and we found the optimum distance. We then found the maximum throughput at varying packet sizes and analyzed the delay and jitter. And for that, we realized that as the packet size increased, the maximum throughput increased and the delay decreased. And then we determined that enabling RTS-CTS handshaking improved the network performance slightly with larger fixed packet sizes. And finally, we analyzed the performance gain overhead from enabling PCF and IEEE 802.11 protocol. And we realized that the delay dropped, the jitter increased, and the throughput decreased when we had the system operating on PCF, all PCF. And the overhead, we found the overhead, which was because the bandwidth was wasted due to the polling overheads, and due to the null packets that are issued in case a poll station does not have any data to transmit. Thank you.